Next speaker is Nikolai Markov from St. Petersburg Polytechnical University with the topic of creation of a software model for calculation the effectiveness of the application of enhanced oil recovery methods for fractured reservoirs.
Okay, thank you very much, Maxime. I will not repeat such a long title. So my talk will be about the project that was recently started with my colleagues. And in the presentation, I will talk about the problem that we have, why technologies for enhanced oil recovery are important. Then we will talk about the model, numerical model that we use in this project. The model was built using T-Navigator software. And we will talk about the problems that we have for the numerical modeling. Then we will talk a little bit about the methods to solve some of our problems, and we will have some more problems. And at the end, we will talk about the results that we have now and about the huge amount of work that we still have in this project. So today, there are a lot of reservoirs that are at the late stages of development. So their peak of productions was far time ago. And the problem is how to increase and change their productions to extend their life. And here we can use so-called enhanced oil recovery methods. And there are a few of them on the left pictures. So there are thermal methods, gas methods, chemical methods, and some other methods, for example, biological. And how it works, you can see on the right picture. It allows us to increase the production of the reservoir. And it's very important for Russian old reservoirs, for example, in West Siberia. So here in this work, we are focusing on the chemical methods, how to use them, and which parameters shall we use to have like the best result. So there are a few types of chemical ER methods. The most popular you can see on this slide. It's polymer floating, alkaline floating, surfactant floating, and the most perspective, ASP floating. This technology involves the sequential injection into the reservoir of surfactants and alkali, then polymers and water. And the general scheme, how it works, you can see on the right pictures. So we're not focusing on a particular method. We want to find which one shall we use in the particular case and what kind of parameters it's better to use. But there are a lot of factors that affect on our choice of the technology. These are petrophysical properties such as permeability, porosity, saturation, and fluid properties, reservoir conditions, and geological properties. So we have a question: how to choose the best method for a reservoir. So we need to analyze all these parameters, how they affect on the final results. And to achieve the goal, we suggest to use the full-scale simulation of the process because it has one big advantage. It's quite accurate and the application area is also quite wide. But the big problem here is that calculation time can be very, very big. So if we want, for example, to solve optimizational problem, it's a big limit for us. So to make it faster, we will try to build surrogate model that needs the data set from the full-scale simulation, and here we have like a big problem to get this data set and to build the model. So the final goal of the project, we want to build such surrogate model trained using the cases obtained by full-scale simulation. Using this surrogate model, we want to be able to calculate dependence of the oil and water production on time for different EORs. And then after that, we need to have an opportunity to choose which method to use for a particular case and with which parameters. And to achieve the goal, we build the very simple model using T-Navigator software. So we consider only a quarter of 5-point water flood pattern, and we have only two wells for the beginning, one production and one injection well. We consider only chemical EORs for this moment, black oil model, oil rim model, and oil porosity and oil permeability model. So just very simple geometry to work with. And here I think you should see the video how it goes in this simple case. So we pump some chemicals into the reservoir, and you can see how saturation changes with time in this case. And what we have, some dependence, for example, the oil and water dependence on time, that we can work with. So we have the numerical model that allows us to generate some results. And to build this model, we use zero flow boundary conditions. And of course, because we need to generate a lot of cases, we use various initial conditions. We choose the mesh step for a number of different parameters values to achieve the needed accuracy within quite a small calculation time, because time is still a big problem. If we need to perform a huge number of calculation, that may cause some limitations for us. But we still have one big problem. We have more than 50 parameters to vary. It's different reservoir parameters, wells production parameters, saturation parameters, fluids parameters, and of course, parameters of our chemical EORs. And we have two big questions. The first one is how to vary this number of parameters, because we don't want to work with 2 power 50 cases. And the second question that we don't answer in this presentation, but we still have it, is how to reduce the number of parameters, because maybe we can consider just a part of them, maybe 20, 25, less number, and of course it will help us a lot. So to solve the first problem, we suggest to use Lysin hypercube here. This is a statistical method for generating a near random sample of parameter values from a multidimensional distribution, and it helps us to bypass the selection of all possible parameters values without repeating. So the example how it looks, you can see on the right picture, and when we have more than 50 parameters, we can imagine it like if we will consider one particular point in this big dimension. Every point will have a unique coordinates, like you can see in this two-dimensional example on the right picture. And why it's so important? Because if we will consider some other sampling methods, for example, if we will consider uniform sampling, we will have a problem with the number of needed cases. But the big advantage that we can work with some nonlinear relationships between the parameters. If we will consider random sampling, we will still have a problem with the number of points, and these methods cannot give us a full image also, because we don't control the parameters distributions here, and we may have some white points where we will don't know about our model behavior. So this also not very good for us. The orthogonal sampling also requires a big number of sample points, and it works not good with nonlinear dependencies. So it's also a problem for us. So the best choice is the Latin hypercube. It allows us to significantly reduce the number of points, and it also allows us to work with different type of parameter distributions. For example, we may have if we have two dependent parameters, you can see how you can see this on the top right picture. So you can see this dependence, and Latin hypercube works fine with them. And for example, if you have one parameter with normal distribution and one parameter with uniform distribution, you can also see that the final distribution with final sampling points are quite good, so they don't cross each other. And the last case, when we have two normal spaces, we also have quite good distribution. And using Latin hypercube, we can significantly reduce the number of points needed. For example, in our case, we now at this moment we work with 5,000 points, so it's much less than 2 power 50 points. And at the moment, we build the Latin hypercube to generate this the number of cases to learn surrogate to train surrogate model, but we still have questions to solve. Because we work with time dependence parameters as an input. And as a result, we want to have also time dependence oil and liquid production for more than 20 years with 1 month discretization. We need the program with a running time not more than 1 minute and the accuracy at least 95%. So it's very challenging problem, and having the reduced number of parameters, we need to decide which machine learning algorithm to use for this problem, and this wasn't solved yet. So I hope we will solve it and put everything together to finalize this scheme and to build the surrogate model that will work quite fast and quite accurate. So what we did at this moment, we built a simple hydrodynamic model for a full-scale modeling and tested. We also built the Latin hypercube-based case generator that allows us to decrease the training sample size required to train the surrogate model. We tested a little bit, yes, but we still need to build the machine learning algorithm that applicable to the problem considered. And of course, finally, we need to build and test the final surrogate model that will allow us to predict the efficiency of using a particular EOR method in a particular reservoir. So thank you very much.
Thank you, Nikolai. We have a time to discussion. Please raise your hand or write in a chat. I see the Nikolai Smirnov can ask a question, please.
Okay, thank you, Dmitry. So, please explain me. You emphasized that all your parameters should be time dependent, and that's why that produces some complexity to your machine learning algorithm. I cannot see the complexity because time is just additional parameter. You have, for example, 5 or 10 parameters. With time, you'll have 11. And then the all machine learning algorithms work as they should do. Or probably I'm missing some very important point. Please.
Okay, thank you very much. Yes, it's a very good question. Of course, time dependence by itself, it's not a big problem here because machine learning algorithms could deal with it. But we have a number of problems. The first problem is still the number of parameters to vary. Even using Latin hypercube, we still have, first of all, we didn't test it like on a full case. So maybe we still need to increase the number of experiments. And some of parameters can have strongly nonlinear dependencies between them. And the biggest challenge is to achieve this accuracy with this number of parameters. So it all works together. And maybe when we will start to work with this case, we will see that everything works fine, and like the machine learning algorithms works fine with our set of cases, and we will not have a problems. But at this point, we expect that we will have a lot of problems to train the final surrogate model.
Okay, thank you. Thank you.
Another questions?
Maxim, I have a question if I can, Dmitry, correct?
Yeah.
So Nikolai, thank you very much. Very interesting presentation. One point which looks really tough in your statement is exactly the account for different EOR mechanisms happening with application of different EOR EOR agents. So if there is a need to employ a machine learning model somewhere in the middle of the whole workflow, you will have many more parameters, like input parameters for the machine learning model, accounting for presence of either special chemicals or miscible gas regimes, or even, I don't know, bias stuff you have mentioned. Have you thought about the approach, how to handle those additional kind of degrees of freedom happening when you are considering the EOR flows within your proxy ML-based model?
Yes, this is, thank you very much. It's also a very good question because we are thinking about it very tough. And that's why for this stage, we just focusing on a very, a few number of methods, because if I understand everything correctly, if we will increase the number of methods allowed to calculate, we will have to improve our scheme that I present here, and of course, I'm 100% sure that it will cause a lot of troubles to us. But here we have also colleagues from Torino Politecnica that maybe they will help us in this problem. Maybe together we will find a great solution how to combine everything together and to build the final model that will work with any kind of methods considered in this project. So.
Yeah, it's just a comment, like, for example, even if you consider a single EOR mechanism, which is miscible gas flow, yes, you may face with a situation where your kind of space of your parameters can grow with additional, like up to 100 parameters easily. And that's what is really tricky about implementing the EOR into the machine learning schemes approximating the simulators. And that's just a comment.
Yeah. Thank you. I got it. Yes, I think we will have a lot of troubles with it. So, and we're still on this step. So we just recently come to this step. So I think we will see everything you said by our own. We will try to implement it. So thank you.
Colleagues, thank you for discussion. I suppose we can discuss later about this topic because it's really a lot of interesting problems we can achieve. So thank you, Nikolai. Thank you, Nikolai Smirnov. Thank you, Dmitry, for discussion.